before we get to vectors and matrices and the like, I'll present some basic mathematical definitions and notations that we're going to use throughout the course. A lot of these that you may already know, so feel free to go through them very quickly or skip over parts you know. A set is an unordered collection of objects. So spades, so hearts, spades, clubs, and diamonds. The order doesn't matter. We use this symbol to mean that an element belongs to a set. So the heart belongs to this set. This means that A is a subset of B. What that means is that every element of the set A is also an element of B. And we say two sets are equal if every element of one is an element of the other. Remember, the order doesn't matter. And a convenient way to prove that two sets are equal is to prove that each is a subset of the other. And the proof usually has that form. First, you'd prove that A is a subset of B, and then you'd prove that B is a subset of A. Here's a notation that we're going to use a lot. Call it a set expression. The set of non-negative numbers would be written like this. The set of all numbers x in the real numbers such that x is greater than or equal to 0. So I use the colon to mean such that. So there are two parts to this expression. The part before the colon, which tells us where these elements come from, and introduces a variable to refer to them so that I can impose conditions in the second part. The second part gives a rule or constraints or conditions that say which of these elements belong to the whole set. There's an analogous Python expression. Let's say this set S is defined to be these integers. The expression x for x in S if x is greater than or equal to 0 gives you only the elements of S that are non-negative. Very often, instead of writing this, we'd write just this. We'd leave out the part that specifies that x is a member of the real numbers if it's supposed to be clear to you that that's where these numbers x are coming from. Here's another example. The set of x such that x squared minus 5 over 6 times x plus 1/6 equals 0. Implicitly, we're talking about real numbers x. And this set consists of just two numbers, 1/2 and 1/3. If a set S is not infinite, we use these vertical bars to denote the number of elements in the set. It's called the cardinality of the set. For example, this set has cardinality 4. Now I introduce the Cartesian product. Given sets A and B, the Cartesian product of A and B is the set of all pairs little a, little b, where little a belongs to big A and little b belongs to big B. So here's an example. We can take the Cartesian product of the set consisting of 1, 2, and the set consisting of hearts, spades, clubs, and diamonds. The Cartesian product is the set of all these pairs. This is named for Descartes, and we'll see him later on in the course. So for example, what's the cardinality of the Cartesian product of A with B in this case? Well, we have two choices for the element of big A and four choices for the element of big B, so we end up with 8 in total. There's a simple rule that if A and B are finite sets, the cardinality of the Cartesian product is the product of the cardinalities of the two sets. So using this, what's the cardinality of this Cartesian product? There are 13 elements in this set and 4 elements in this set. So the cardinality of the Cartesian product is 52. This expression denotes the set of all pairs of real numbers in which the second equals the square of the first. And of course, we might abbreviate that in this way, leaving out this part. So just the set of pairs x, y such that y equals x squared. You're supposed to guess from the context that x and y are elements of the real number. Here's another example. the set expression tells us that the set consists of all triples x, y, and z, where x, y, and z are elements of the real numbers, such that x is greater than 0 and y is greater than 0 and z is greater than 0. That is, it's the set of all triples of non-negative real numbers. You're supposed to interpret the comma here as an and. All the conditions on the right have to be satisfied for the triple to belong to the set. And as before, we might abbreviate that by leaving out this part and write it in this way. What's a function? Well, intuitively, a function for each input element in a set A, a function assigns a single output from another set, B. And in this context, A is called the domain of the function, and B is called the codomain. Formally, in math, a function is often defined as a set of pairs AB, no two of which have the same first element, A. So here's an example. The function with domain 1, 2, 3, and so on that doubles its input is represented by this set of pairs. The first element of the set is the pair 1, 2. The second is 2, 4, and so on. Here's another example. In this case, the domain is the Cartesian product of the positive integers with itself. And this function involves multiplying the two elements that form its input. So 2 times 2 is 4, 2 times 3 is 6, and so on. Now, the output for a given input is called the image of that input under the function. The image of q under the function f is denoted f of q. This should all be very familiar. And we would say that if f of q equals r, we say that q maps to r under f. In Mathes, we write it this way. Q maps to R. So this symbol represents maps to. Now remember that the set from which the outputs are all chosen is the codomain. We use this notation to mean that f is a function whose domain is D and whose codomain is f. Now we have some flexibility in defining a function as to the choice of the codomain. We're allowed to have elements in the codomain that are not images of any elements in the domain. Here's a quick example. Caesar cryptosystem. The Caesar cipher. Each letter is mapped to the one 3 steps ahead. So matrix would map to Pudwala. So the function mapping letter to letter can be written in this way. It maps A to D, B to E, C to F, and so on. And we might use a diagram like this to represent that same function. A maps to D, B maps to E, and so on. In this case, both the domain and the codomain are the letters A through Z. Now, the image of a function is the set of all the images of the inputs, the images of elements of the domain. It's written im of f. For example, the cosine function. We can define the cosine function to have the domain, the set of real numbers, and the codomain also the set of real numbers. However, the image of the cosine function is just those real numbers that lie between -1 and 1, because those are the only numbers that are the images under the function cosine of elements of the domain. And notice that the image in this case is not the same as the codomain. Now, the image of the Caesar encryption function is A through Z, which is the same as the codomain. Here's another example depicted here. The domain is the numbers 1 through 4, and the codomain is A, B, C, D, and E. And you notice the image of this function is the set A, B, C, and E. D is not in the image because there's no element of the domain that maps to it. You might be familiar with the term range. Some people use range to mean the codomain of a function, and some people use range to mean the image. Because there's this confusion, I tend to avoid the word range altogether. So I just use codomain and image. For sets f and d, f to the power of d represents all the functions from d, the exponent, to f. So, for example, the set of all functions from the set of words in some language to the set of real numbers would be written in this way, r to the w. And note that for finite sets, the cardinality of f to the d equals the cardinality of f to the power of the cardinality of d. For any domain D, any set, there's an identity function written ID, sometimes with a subscript, the domain. Its domain is D, its codomain is D, and it simply maps each element of the domain to itself. So here's an example. It maps the integers 1, 2, 3, and 4 to the integers 1, 2, 3, and 4. It's not very interesting, but it's useful in the next definition. Now, for functions f with domain A and codomain B, and g with domain B and codomain C, the functional composition of f and g is the function which we write g composed with f. The domain is A, and the codomain is C, and it's defined in this way. G composed with f applied to an input x is g applied to the result of f applied to x. So, for example, here's a function f whose domain is 1, 2, 3, and the codomain is a, b, c, and d. Here's a function g whose domain is a, b, c, and d, and whose codomain consists of 4 and 5. Here's, when we compose them, we get this function. This is g composed with f. It takes elements from the domain of f and maps them to elements of the codomain of g. Here's another example. If g is the function that squares its input and f is the function that adds 1 to its input, g composed with f applied to x is x plus 1 squared. Now let's use composition to derive the Caesar encryption function. First, we define the function f by mapping a to 0, b to 1, c to 2, and so on. Define g to be the function that adds 3 mod 26, and define h to be the function that goes back from the integers 0 through 25 to the letters a through z. Then h composed with g composed with f is the Caesar encryption function. So here are the three functions indicated, and here's the function we get by composing all of them together. The parentheses are not needed because function composition satisfies associativity. This is what associativity means. H composed with the result of composing g with f is the same as h composed with g composed with f. Simple proof, for any element x of the domain of f, if we take h composed with the composition of g and f and apply it to x, that's the same as h applied to the result of applying the composition of g and f to x. And that's the same as applying h to the result of applying g to the result of applying f to x. And then we can unfold that to get the other form. We say that functions f and g are functional inverses of each other if f composed with g and g composed with f are defined and are identity functions. And a function that has an inverse is called an invertible function. Now, a function f from d to f is said to be one-to-one if f of x equals f of y implies x equals y for every x and y in the domain. That means that there are no two distinct elements that have the same image. So here's a picture of a function that's not one-to-one, because these two elements of the domain have the same image. A function f is onto if for every z in the codomain there exists an element, say A, in the domain that maps to Z under that function. So here's an example of a function that is not onto, because here's an element in the codomain that's not the image of any element in the domain. Now, invertible functions are one-to-one. Here's the proof. Suppose you have an invertible function f and it's not one-to-one. So there exist two elements, x1 and x2, that are different, where they have the same image, y, under f. Well, what's the inverse of f? The inverse of f applied to y is x1, but the inverse of f applied to y is also x2, by definition of the inverse. And both can't be true. A function, such as f inverse, has to have only one image for each input. So that proves the proposition. Similarly, invertible functions are onto. Suppose you have an invertible function f and it's not onto. So there exists some element, say y hat, in the codomain that's not the image of any element in the domain. Well, let's consider the inverse, f inverse. This is a function, so on input y hat, it has some output, some value x hat in the codomain of f inverse, that is in the domain of f. By the definition of inverse, that would mean that f maps x hat to y hat. But that's a contradiction, so that proves the proposition. In fact, and this is an important theorem we'll use, a function is invertible if and only if it is one-to-one and onto. The proof is fairly simple. It uses the two propositions we just saw and a little bit more work. That means that if a function is invertible, it's one-to-one and onto. We already saw that. And if a function is one-to-one and onto, it's invertible. A procedure is a description of a computation that, given an input, produces an output. So here's an example. A computational problem is an input-output specification that a procedure might be required to satisfy. For example, one that we'll look at later is integer factoring, where the input is an integer, m, greater than 1, and the output is a pair of integers whose product is m. Now, there are some differences between these ideas. Functions and computational problems don't tell us how to compute an output from an input, whereas a procedure does. And there might be multiple procedures satisfying for the same spec, so solving the same computational problem. A computational problem might allow several outputs for each input. That's true of this integer factoring problem, for example. And the same procedure can be used to compute different functions. In this course, we'll write procedures in Python. For example, this is the definition of a procedure to multiply the two inputs. You might be used to calling these procedures functions, but we're going to reserve the term function to refer only to the mathematical object. Now, in Python, we will often use a structure called a dictionary to represent a function whose domain is finite. For example, the function depicted here can be represented by this dictionary. It maps a to 4, b to 4, c to 5, and d to 5. Now, a special kind of function is a probability distribution function. It's used to specify the relative likelihood of different outcomes of a single experiment. It assigns a probability, which is a non-negative number, to each possible outcome, and the probabilities of all the possible outcomes must sum to 1. So, for example, in the game of Scrabble, at the very beginning, the bag is filled with tiles. There are 9 A's, 2 B's, and so on. So at the very beginning, consider the experiment of drawing a tile from the bag. Since the total number of tiles is 98, the probability of drawing an E is 12 over 98 because there are 12 E's. The probability of drawing an A is 9 over 98, and so on. The denominator is 98 so that all these probabilities will sum up to 1. We represent that function by this Python expression. Often, the probability distribution is what's called a uniform distribution, which simply means that it assigns the same probability to all the outcomes. So, for example, rolling a die, the possible outcomes are 1 through 6, and the probabilities are all the same. They all have to be 1/6, because remember, probabilities have to sum to 1. In Python, you'd represent this function by this dictionary. Maps 1 to 1/6, 2 to 1/6, and so on. Another example, to model the flipping of two coins. The possible outcomes are heads, 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 tails, tails, heads, and tails, tails. And the probabilities are all 1/4. We represent that function in Python by this dictionary. It maps the pair heads, heads to 1/4, and so on.